Welcome to today's Explainer. You know, it really does feel like absolute magic when a chatbot just effortlessly answers some wildly complex question or when a car literally drives itself down the highway. But I promise you, there is zero magic involved. Today, we're going to completely demystify the machine's mind. We're going to break down the logic, the hidden structures, and the exact training processes behind artificial intelligence. We're focusing entirely on how these systems actually acquire knowledge. And don't worry, we're going to do it all without drowning in heavy, complicated computer science jargon. So let's get into it. All right, let's quickly map out our journey for today. We're going to cover the AI learning hierarchy, 3 ways machines learn, inside a neural network, the engine of learning, training large language models, and finally, the human touch. First up, Section 1, the AI learning hierarchy. Before we really dive into how machines learn, we've got to get our vocabulary straight. You hear these buzzwords everywhere, right? Artificial intelligence, machine learning, deep learning. The media throws them around constantly, and honestly, they're often used completely interchangeably, which is totally incorrect. Think of these concepts like nested dolls. Artificial intelligence is that outermost, broadest doll. It encompasses literally any system designed to emulate human reasoning and problem solving. Pop that open, and inside you have machine learning. This is a specific subset, focused purely on algorithms that learn from data to make predictions, rather than relying on strict rules written by humans. And then, nestled deep inside that one is deep learning, an even more specialized subset that uses complex, multi-layered neural networks, completely inspired by the human brain, to handle just massive volumes of data. Now, traditionally, if you wanted a computer to do something, a human programmer had to explicitly write the code to tell it exactly what to do, step by step. But with machine learning, we completely flip the script. The algorithm just ingests a massive amount of historical past data. And from that data, the machine actually builds its own logical model. It detects all these underlying patterns that are completely invisible to the human eye. So when you eventually feed it brand new data, it can accurately predict the output all on its own. It's a real game changer. But, we have to ground ourselves in reality here. While machine learning gives us the incredible superpower of automating complex tasks and predicting things like customer behavior, there are definitely trade-offs. These systems are incredibly hungry for data. If you don't have good data, well, you don't have a good model. Plus, there's always the possibility of high error rates, not to mention the massive amount of time and computational space required just to train these systems in the first place. Moving right along to Section 2, 3 ways machines learn. Okay, so we know machine learning needs data to build predictive models. But how do machines actually extract knowledge from that data? Basically, they do it in one of 3 distinct ways. First up is supervised learning. This is where the machine is trained on data that humans have already neatly labeled for it. It's kind of like teaching a kid with flashcards, so they can eventually, say, forecast future sales. Next is unsupervised learning. Here, the machine is just thrown into a vast sea of raw, completely unlabeled data, and it has to figure out the hidden patterns all by itself, like sorting similar customers into groups. And finally, there's reinforcement learning. This one is absolutely fascinating. It's a system of trial and error where the AI acts like an agent in an environment. It earns a reward for doing the right thing and a penalty for doing the wrong thing. It's literally exactly how a robotic dog learns to coordinate its legs and walk. Part 3, inside a neural network. Now, when learning tasks get super complex, like recognizing faces or understanding human language, we have to zoom in further and use deep learning, which runs on something called a neural network. Drawing inspiration directly from biological brains, these networks stack artificial neurons, or nodes, into distinct layers. You've got an input layer that takes in the raw data, multiple hidden layers that do all the heavy lifting to transform and process that data, and finally, an output layer that delivers the final prediction. Think of a standard spam filter. The input layer spots words like prize or money. The hidden layers evaluate the context around those words, and the output layer makes the final call on whether it's spam. To actually make these complex decisions, the network relies on 2 fundamental parameters, weights and biases. Think of weights as little volume dials that tune the importance of an input. The word prize gets a heavier weight, turning that dial way up, compared to a normal word like hello. Biases, on the other hand, act as built-in thresholds. They can shift a decision up or down, allowing a neuron to fire off and activate, even if the input signals coming in are relatively weak. Together, these dials and thresholds are the exact things the network is trying to learn and carefully calibrate over time. Which brings us perfectly to Section 4, the engine of learning. So if weights and biases are the physical dials of our machine,
how does the neural network actually know how to tune them? How does it, learn? Well, whenever the network makes a guess during training, it checks its prediction against the true answer. It then uses what's called a loss function to calculate its error. Essentially, this loss function is just a mathematical measurement asking, just how badly did I miss the mark? And the fundamental goal of the entire learning process is simply to minimize that loss.
And that leads us to an incredibly powerful algorithm called backpropagation. This four-step loop right here is the literal engine of learning. First, the forward pass. The network makes its initial prediction. Second, error calculation. It measures its loss. Third, the backward pass. It propagates that error information backwards through all those layers of neurons. And finally, the weight update. It slightly tweaks and adjusts all those dials, the weights and biases, to fix the error. It just repeats this loop over and over, millions of times across massive datasets, getting a little bit smarter every single time. Section 5. Training large language models. Okay, so what happens when we take this incredible learning engine and we scale it up with an unimaginable amount of data and raw computing power? We get the modern AI that we interact with every single day. Large language models. Now, you've definitely heard of ChatGPT for sure, but GPT is actually an acronym that perfectly describes the model's learning structure. Generative means it doesn't just classify old data, it creates completely new text. Pre-trained means it learns broad general language patterns from the vast internet before we ever adapt it to specific tasks. And Transformer refers to a revolutionary architecture from 2017 that processes all this data in parallel, allowing for massive scale and a crazy deep understanding of context. And just look at how smoothly scaling up data and compute power improved these models over time. Back in 2018, GPT-1 was basically just a proof of concept. But by 2020, GPT-3 was so massive that a totally new behavior emerged, fuse-shot prompting. The model could suddenly learn a brand new task just by seeing a couple of examples directly in the text prompt itself. Then in 2022, Instruct GPT was specifically trained to actually follow human directions. And late that same year, ChatGPT came along, providing a simple, multi-turn shot interface that basically turned a research project into an everyday global tool capable of wildly complex reasoning. Finally, Section 6, the human touch. But here is the catch. A raw GPT model trained purely on the wild open internet can be highly chaotic. I mean, it's essentially just predicting the next word based on billions of random web pages, which means it can be unhelpful, super strange, or even outright toxic. As these models scaled, researchers slammed right into what's known as the alignment problem. This was the rather terrifying realization that a model's raw predictive behavior wasn't reliably aligned with actual human intentions, safety expectations, or our values. A raw neural net doesn't care if an output is polite, it just cares about statistical probability. We absolutely needed a way to tame it. So, to bridge this gap, they brought humans back into the loop. First, they use supervised fine-tuning. This is where human experts literally sit down and write out ideal responses for the AI to imitate. Then, they use reinforcement learning from human feedback, or RLHF. Here, humans look at different AI outputs and rank them. The network learns from these rankings, creating a reward model that naturally optimizes the AI to produce helpful, polite, and safe answers. This human touch is exactly what transforms a chaotic, babbling text predictor into the reliable conversational assistant we use today. Which brings us to the bleeding edge of where we are today. We've seen exactly how machines take data, calculate their errors, adjust their weights, and learn from human feedback. But I want to leave you with this somewhat provocative thought. What happens to the trajectory of AI learning when these models become so incredibly advanced that they no longer even require human feedback to correct their own errors? If an AI can eventually generate its own training data and build its own reward models, what does the next evolution of the machine's mind actually look like? It's something to think about. Thank you so much for joining me on this explainer today, and as always, keep learning.